December 20th, 1944. The snow-covered forests of the Ardennes trembled under the thunder of German artillery. In a makeshift laboratory carved into the basement of a captured Belgian farmhouse, 3 Axis scientists hunched over a metal object no larger than a coffee cup. Dr. Wilhelm Kramer adjusted his wire-rimmed glasses and peered at the device that had been extracted from an unexploded American shell just hours before. His hands trembled slightly as he turned the cylindrical mechanism, noting the intricate electronic components visible through the damaged casing. The smell of cordite and cold concrete filled the cramped space as Kramer's colleague, Dr. Hiroshi Tanaka, leaned closer with a magnifying glass. What they were about to discover would shatter every assumption they held about American technological capability. The third man, Italian engineer Dr. Marco Benedetti, had been silent for nearly 10 minutes, simply staring at the device with growing horror. None of them spoke as the implications became clear. The war they thought they were winning had been lost months ago, and this small metal cylinder was the proof. No one in the German High Command knew that, in this frozen cellar, 3 of their finest minds were about to confirm their worst fears about American ingenuity. The story of this moment began 2 years earlier in a cluttered workshop in Dayton, Ohio, where a stubborn engineer named Lysander Kowalski refused to accept that his country's anti-aircraft defenses were failing. Kowalski came from the kind of Polish immigrant family that believed in solving problems through relentless work and creative thinking. His father had been a machinist who could fix anything with moving parts, and his mother had managed the household budget with mathematical precision that would have impressed an accountant. When young Lysander showed an aptitude for both electronics and stubborn determination, his parents scraped together every dollar to send him to Carnegie Tech. He graduated in 1938 with a degree in electrical engineering and a reputation for questioning authority when conventional wisdom didn't match observed reality. His professors remembered him as the student who would stay after class to argue about theoretical limitations, often proposing solutions that seemed impossible until he built working prototypes in his dormitory room. When Pearl Harbor thrust America into the war, Kowalski was working for a small electronics firm in Ohio, designing radio components for civilian applications. The call for technical expertise in military applications reached him through a Navy recruitment office in Cleveland, where a harried lieutenant commander was desperately seeking engineers with electronics experience. Kowalski enlisted immediately, but not before spending 3 sleepless nights in his workshop, sketching ideas for electronic devices that might give American forces an advantage against enemies who had been preparing for war for years. His early military assignments involved routine maintenance of existing radar systems, work that frustrated him because he could see obvious improvements that regulations prevented him from implementing. Fellow technicians noticed that Kowalski would often work late into the night, not on assigned tasks, but on unauthorized modifications to equipment that consistently improved performance. His commanding officers were torn between appreciation for his results and concern about his tendency to ignore standard procedures. He had no idea that soon this willingness to circumvent official channels would lead to a breakthrough that would fundamentally alter the balance of power in the war. The larger context surrounding Kowalski's work was a desperate Allied struggle against Axis air superiority and artillery effectiveness. By 1942, German U-boats were devastating Allied shipping in the Atlantic. Japanese aircraft dominated Pacific skies, and Axis artillery units were achieving devastating accuracy against Allied positions across multiple theaters. Traditional anti-aircraft guns required direct hits to bring down enemy aircraft, a feat that demanded extraordinary skill and often relied more on luck than precision. Artillery barrages against enemy positions were similarly inefficient, with most shells exploding harmlessly against the ground, rather than at the optimal height to maximize casualties and destruction. Military strategists estimated that conventional fusing methods achieved effective results less than 15% of the time, a statistic that translated into thousands of unnecessary Allied casualties and prolonged campaigns that drained resources and morale. Intelligence reports from the European theater describe German artillery units achieving nearly twice the effectiveness of comparable American positions, largely due to superior targeting methods and more reliable fusing mechanisms. The mathematical reality was stark. Allied forces were consuming ammunition at unsustainable rates while failing to achieve decisive tactical advantages in most engagements. American military leadership understood that technological innovation would be essential to victory, but the traditional development process moved too slowly to address urgent battlefield needs. Standard procurement procedures required months of testing and approval before new designs could be implemented, while enemy forces continued to refine their existing advantages. Senior commanders faced an impossible choice between maintaining safety protocols that ensured reliability and accepting risks associated with accelerated development cycles. The stakes extended far beyond individual battles. The entire strategic timeline of the war depended on achieving technological parity with enemies who had spent years perfecting their military capabilities. Intelligence estimates suggested that prolonged conventional warfare would favor Axis powers who controlled substantial manufacturing resources and had demonstrated superior coordination between research and field implementation. Allied victory required not just matching enemy capabilities, but achieving clear technological superiority that could offset numerical and geographical disadvantages. The pressure to innovate was immense, and failure would mean accepting casualties and strategic setbacks that might prove insurmountable. Kowalski's opportunity came during a routine inspection of damaged anti-aircraft equipment at a training facility in Maryland. The facility commander, Colonel Thaddeus Wickham, had become increasingly frustrated with the poor performance of conventional time-delay fuses, which required gunners to estimate aircraft speed and distance with impossible precision. During a particularly disastrous training exercise where experienced crews failed to hit even slow-moving practice targets, Wickham gathered his technical staff to discuss alternatives to existing procedures. Kowalski was the most junior member of the group, but his background in electronics made him the only person present who understood the theoretical possibility of electronic fusing mechanisms. When senior officers dismissed electronic solutions as too complex for battlefield conditions, Kowalski remained silent but began sketching circuit designs on the margins of his training manual. After the meeting, he approached Colonel Wickham privately and requested permission to experiment with electronic alternatives during off-duty hours. Wickham was initially skeptical, but agreed to provide access to workshop facilities, warning Kowalski that any unauthorized modifications to official equipment would result in immediate court-martial proceedings. Working alone in the workshop after midnight, Kowalski began developing what would eventually become the most closely guarded technological secret of the war. His initial concept was elegantly simple. Instead of relying on time delays, artillery shells could carry radio transmitters that would detect nearby objects and detonate automatically when optimal proximity was achieved. The technical challenges were enormous, requiring miniaturized electronic components that could withstand the tremendous acceleration forces experienced during firing, while remaining sensitive enough to detect aircraft at effective ranges. Existing radio technology was far too bulky and fragile for artillery applications, but Kowalski believed that innovative circuit designs could overcome these limitations. His first prototype was crude but functional, consisting of a simple oscillator circuit connected to an antenna system that could fit inside a modified practice shell. Initial tests were conducted in secret using equipment that Kowalski borrowed from various sources without official authorization. The results were promising enough to convince him that the concept was viable, but he knew that developing a practical system would require resources and support that exceeded his current authority. The breakthrough came when Kowalski realized that conventional thinking about electronic complexity was fundamentally flawed for this application. Instead of trying to create sophisticated detection systems, he focused on designing the simplest possible circuit that could reliably identify changes in electromagnetic environment, indicating nearby objects. His innovation involved using the shell's metal casing as part of the antenna system, creating a resonance effect that would change detectably when the shell passed close to aircraft or other metallic targets. This approach eliminated the need for complex calibration procedures while ensuring that the device would function reliably under battlefield conditions. Testing this concept required violating several regulations about unauthorized use of military equipment, but Kowalski decided that the potential benefits justified the risks to his military career. Working through the night on Christmas Eve, 1942, he completed a prototype that successfully demonstrated proximity detection at ranges exceeding 300 feet. The implications were staggering. Artillery units equipped with these devices could achieve hit rates approaching 90%, transforming every gun position into a deadly accurate defensive system. Colonel Wickham's reaction to Kowalski's demonstration was immediate and decisive. Despite concerns about regulatory violations, he recognized that this innovation could fundamentally alter anti-aircraft effectiveness across all theaters of operation. However, the path from prototype to production would require navigating a complex bureaucracy that typically moved far too slowly to address urgent military needs. Wickham made the controversial decision to contact the National Defense Research Committee directly, bypassing normal channels and risking his own career to expedite evaluation of Kowalski's invention. The committee's initial response was skeptical, as their experts believed that electronic components could not withstand artillery firing conditions without sophisticated protective measures that would make the devices too expensive for widespread use. Wickham arranged a demonstration at the Aberdeen Proving Grounds, where Kowalski would have one opportunity to prove that his approach could work under actual firing conditions. The pressure was enormous. Failure would not only end the project but would likely result in court-martial proceedings for both men. The demonstration on January 15, 1943, exceeded every expectation. Kowalski's proximity fuses achieved hit rates that shocked even the most optimistic observers, destroying practice targets with consistency that conventional methods could never approach. The attending officials immediately classified the entire project as top secret and authorized emergency production procedures that would bypass standard testing protocols. Kowalski found himself transferred to a classified facility where teams of engineers and technicians worked around the clock to refine his basic design for mass production. The urgency was driven by intelligence reports indicating that enemy forces were developing similar technologies, creating a technological arms race where American superiority would depend on achieving production before Axis scientists could complete their own projects. Within 6 months, American factories were producing thousands of proximity fuses monthly, each one incorporating innovations that Kowalski had originally developed in violation of standard procedures. The first combat use of proximity fuses occurred during Allied operations in the Solomon Islands, where Japanese aircraft had been achieving devastating effectiveness against American positions. Naval anti-aircraft crews equipped with the new technology achieved immediate success rates that seemed almost miraculous compared to previous engagements. Japanese pilots reported encountering defensive fire that seemed impossibly accurate, with shells exploding precisely at the moment of greatest effectiveness rather than at predetermined intervals that could be predicted and avoided. Intelligence reports from captured enemy personnel revealed growing concern about American technological capabilities that exceeded previous estimates. The psychological impact was as significant as the tactical advantage. Enemy forces began avoiding engagements where they had previously held clear superiority. Word of this success spread quickly through classified channels, leading to accelerated deployment across all theaters where American forces faced air attacks. By December 1944, when German forces launched their massive offensive in the Ardennes, American artillery units throughout the region were equipped with proximity fuses that had already demonstrated their effectiveness against enemy aircraft and ground targets. The Battle of the Bulge would provide the most comprehensive test of this technology under extreme combat conditions, as German forces committed their remaining reserves in a desperate attempt to achieve decisive victory before American industrial capacity could make Axis victory impossible. What German commanders did not know was that their offensive would encounter defensive capabilities that exceeded anything they had previously faced, largely due to innovations that had originated in an Ohio workshop where one stubborn engineer had refused to accept conventional limitations. The scale of German commitment to this offensive meant that captured American equipment would inevitably fall into enemy hands, providing Axis scientists with their first opportunity to examine technology that their intelligence services had only heard about through fragmentary reports. Dr. Wilhelm Kramer had spent most of his career developing electronic systems for German military applications, but nothing in his experience had prepared him for what he discovered in that Belgian basement. The proximity fuse he examined displayed engineering sophistication that challenged his assumptions about American industrial capabilities. The miniaturization of electronic components exceeded anything achieved by German technicians, despite having access to some of the world's most advanced manufacturing facilities. More disturbing was the evidence that these devices were being produced in enormous quantities. Intelligence estimates suggested that American forces were using proximity fuses for routine artillery missions, rather than reserving them for critical targets. This implied manufacturing capacity and resource allocation that dwarfed German production capabilities across all electronic applications. Kramer realized that American industry had achieved technological superiority through innovations that German scientists had considered theoretically impossible under battlefield conditions. Dr. Hiroshi Tanaka brought a different perspective to the analysis, having worked extensively on Japanese electronic warfare systems that emphasized simplicity and reliability over sophisticated performance. What shocked him about the American fuse was not its complexity, but its elegant simplicity. The circuit design achieved maximum effectiveness through minimal components, demonstrating engineering philosophy that prioritized practical implementation over theoretical perfection. This approach allowed mass production using standard manufacturing techniques rather than requiring specialized facilities that limited production quantities. Tanaka understood that this philosophy represented a fundamental difference in development strategy. While Axis engineers focused on creating sophisticated systems that required extensive training and maintenance, American designers had created devices that could be operated by ordinary soldiers without specialized knowledge. The implications extended far beyond artillery applications. This engineering approach could be applied to any military technology, giving American forces systematic advantages across all categories of equipment. Dr. Marco Benedetti's analysis focused on manufacturing evidence visible in the fuse construction. The precision of component placement and the consistency of soldered joints indicated automated production processes that far exceeded European capabilities. More significantly, the materials used in construction suggested access to specialized alloys and electronic components that Axis forces had been unable to obtain since 1942 due to resource shortages and supply disruptions. The Americans were not merely matching Axis technological capabilities. They were operating with manufacturing infrastructure and resource access that made sustained technological competition impossible. Benedetti estimated that producing equivalent devices would require retooling entire factories and obtaining materials that were no longer available to Axis forces. Even if German engineers could reverse engineer the American design, implementation would require industrial capacity that no longer existed within territories under Axis control. The three scientists spent the remainder of that night documenting their findings in a report that would reach German High Command within 48 hours. Their conclusions were devastating. American technological capabilities exceeded previous intelligence estimates by margins that made continued resistance strategically impossible. The proximity fuse represented not just one innovation, but evidence of systematic advantages in research, development, and manufacturing that would only increase as the war continued. German forces were not merely falling behind in a technological arms race. They were competing against opponents who had achieved superiority across all categories of military technology. The mathematical reality was inescapable. Continued warfare would result in increasingly disproportionate casualties as American technological advantages expanded. The war could still continue for months or even years, but ultimate outcome was no longer in doubt. When dawn broke over the Ardennes on December 21, 1944, the German offensive was already beginning to falter against defensive positions that demonstrated technological superiority that Axis commanders had never encountered. American artillery units equipped with proximity fuses were achieving casualty rates that broke up German formations before they could reach their objectives. The psychological impact on German troops was immediate and devastating. Veterans who had survived the years of combat reported that American defensive fire seemed impossibly accurate, as if every shell was individually guided to its target. Unit cohesion began breaking down as soldiers lost confidence in their ability to achieve tactical objectives against opponents who seemed to possess supernatural accuracy. Field commanders requested immediate intelligence assessments to explain American capabilities that exceeded all previous encounters. The broader implications of proximity fuse technology extended far beyond individual battles or campaigns. Intelligence reports reaching Berlin described American production facilities capable of manufacturing these sophisticated devices in quantities that suggested unlimited supply. This meant that American forces could use proximity fuses for routine missions, where German forces would have been forced to conserve such valuable technology for only the most critical targets. The economic implications were staggering. While Axis forces struggled to maintain production of conventional ammunition, American industry was casually producing electronic devices that represented the highest levels of technological sophistication. German economists calculated that the raw materials required for a single proximity fuse could produce dozens of conventional shells, yet Americans were using these devices for routine artillery missions against ordinary targets. Kowalski never learned about the impact his invention had on enemy morale and strategic planning. By the time Axis scientists were examining captured proximity fuses, he was working on even more advanced projects in classified facilities where his reputation for innovative problem-solving had earned him significant autonomy. His willingness to ignore regulations in pursuit of effective solutions had become an unofficial model for other military researchers, who discovered that breakthrough innovations often required circumventing standard procedures that prioritized caution over urgency. The culture of authorized rule-breaking that Kowalski had pioneered was spreading throughout American military research, accelerating development cycles and producing technologies that consistently surprised enemy intelligence services. His original violation of workshop protocols had evolved into a systematic approach that gave American forces technological advantages across multiple domains. The psychological transformation of enemy forces began with individual soldiers who reported encountering weapons that seemed impossibly effective. but eventually reached senior commanders who realized that continuing resistance was tactically hopeless. German field reports described American artillery achieving accuracy rates that experienced officers knew were mathematically impossible using conventional fusing methods. These reports created a feedback loop of declining morale and reduced tactical effectiveness as German units became reluctant to engage American positions where they had previously held advantages. Intelligence assessments describing American technological capabilities began influencing strategic decisions as German commanders recognized that prolonged warfare would only increase their disadvantages as American production capacity continued expanding. The Proximity Fuse program also demonstrated how individual initiative could reshape entire strategic paradigms when supported by institutional flexibility. Kowalski's unauthorized experiments became the foundation for production programs that employed thousands of workers and consumed enormous resources, but only because military leadership was willing to accept risks associated with unproven technologies. This willingness to bet on innovative solutions rather than relying on established methods gave American forces systematic advantages that compounded over time. Each successful innovation encouraged further experimentation, creating a culture of technological optimism that contrasted sharply with Axis approaches that emphasized incremental improvements to existing systems. The result was a technological momentum that accelerated throughout the war, producing advantages that enemy forces could not match or counter. By the spring of 1945, proximity fuses had become standard equipment for American artillery units across all theaters, fundamentally altering tactical calculations that had governed military operations since the beginning of the war. Enemy forces could no longer rely on traditional approaches to attacking fortified positions, as American defensive fire achieved effectiveness that made conventional assault tactics suicidal. The technology that had originated with one engineer's refusal to accept standard limitations had evolved into a systematic advantage that influenced every aspect of military operations. Intelligence reports from the final months of the war described enemy units that simply refused to engage American positions where proximity fuses were known to be deployed, creating tactical situations that would have been impossible under previous technological conditions. The broader lesson of Kowalski's innovation extended beyond military applications to questions about institutional culture and individual initiative. His success demonstrated that breakthrough innovations often required individuals willing to accept personal risks in pursuit of solutions that conventional wisdom considered impossible. The military bureaucracy that initially opposed his unauthorized experiments eventually became the mechanism for implementing his innovations on a massive scale, but only after his results proved that regulatory concerns were less important than tactical effectiveness. This transformation suggested that institutional success required balancing legitimate concerns about safety and reliability with recognition that urgent problems demanded solutions that might not conform to established procedures. The challenge was creating organizational cultures that encouraged appropriate risk-taking while maintaining necessary standards for quality and reliability. The final irony of the proximity fuse story was that its most significant impact might have been psychological rather than tactical. While the technology certainly improved American military effectiveness, its greater importance lay in demonstrating American technological capabilities that exceeded enemy expectations by enormous margins. Axis forces had expected to face opponents with superior numbers and resources, but had assumed technological parity that would allow skilled troops to achieve tactical victories despite strategic disadvantages. The proximity fuse shattered these assumptions by proving that American innovation was producing weapons that made traditional tactics obsolete. This realization created a cascade of doubt and demoralization that influenced strategic decisions and unit performance across all theaters where Axis forces encountered American technology. When the war ended in August 1945, Kowalski returned to civilian life with decorations and commendations that could never be publicly discussed due to the classified nature of his contributions. He found work with an electronics company in Detroit, where he spent the next 30 years developing commercial applications for technologies that had originated during his wartime research. His colleagues knew him as a quiet man who seemed unusually creative when confronting technical problems, but few suspected that his innovations had influenced the outcome of the war. Letters from former military colleagues occasionally reminded him of the lives saved and battles won through his willingness to ignore regulations in pursuit of effective solutions, but he rarely discussed his wartime experiences even with family members who had security clearance for such conversations. The proximity fuse became a standard topic in military engineering courses after the war, where students learned about the technical principles involved in radio-controlled detonation systems. However, the human story of individual initiative and institutional adaptation that made the technology possible was often omitted from these technical discussions. Military historians focused on production statistics and tactical effectiveness, while overlooking the personal courage required to challenge established procedures when lives depended on finding better solutions. The engineering achievements were impressive, but the more important lesson involved the willingness of individuals to accept personal risks when institutional barriers prevented necessary innovations. This lesson remained relevant long after the specific technology became obsolete, as subsequent conflicts required similar combinations of technical creativity and bureaucratic courage. The captured proximity fuses that Axis scientists examined in December 1944 became symbols of technological superiority that influenced post-war assessments of American industrial capabilities. Intelligence services studying these devices realized that the war had been decided by innovations that their own research programs had never seriously considered. The gap between American achievements and Axis expectations was so enormous that it called into question fundamental assumptions about technological development and strategic planning. The devices that seemed impossibly sophisticated in 1944 became routine components in post-war military systems, but their psychological impact on enemy confidence had already achieved strategic effects that continued influencing international relations for decades after the original conflict ended. Perhaps the most lasting significance of Kowalski's innovation was its demonstration that individual creativity could achieve results that massive institutional programs had failed to produce. While enemy forces invested enormous resources in developing sophisticated weapon systems, one American engineer, working alone in an unauthorized workshop, had created technology that neutralized these advantages through elegant simplicity rather than overwhelming complexity. This suggested that institutional success required not just adequate funding and competent management, but also cultural attitudes that encouraged individual initiative and tolerated reasonable risks in pursuit of breakthrough solutions. The proximity fuse proved that the most important military technology might emerge from unexpected sources when creative individuals were given opportunities to challenge conventional wisdom. Today, the principles underlying proximity fusing technology are standard components in military systems that most people take for granted, but the personal story of innovation under pressure remains an inspiration for anyone confronting seemingly impossible technical challenges. Kowalski's willingness to risk his career in pursuit of solutions that might save lives demonstrated the kind of moral courage that transforms individual initiative into collective advantage. His story reminds us that breakthrough innovations often require individuals willing to accept personal consequences for challenging institutional limitations that prevent necessary progress. In a world where technological competition continues determining strategic outcomes, the example of one stubborn engineer who refused to accept conventional limitations remains as relevant today as it was in that Belgian basement where enemy scientists realized they had already lost the war. Would you have been willing to risk everything on an unauthorized experiment that might change history? The courage to break rules in service of higher principles remains the foundation of progress in every field where human ingenuity confronts institutional inertia. Share this story to honor the unsung heroes whose quiet rebellions saved lives and changed the world, one unauthorized innovation at a time.